SQL views. 1. Definition of SQL views. A view in SQL is a virtual table based on a SQL query. It is a saved query that users can treat as a regular table. Views do not store data physically, but provide a way to represent data in a specific format or perspective. 2. Creating a view. Use the create view statement. Syntax: create view underscore name as select column 1, column 2, from table underscore name where condition. This creates a new view based on the result set of the select statement. 3. Advantages of using views. Views simplify complex queries, improve data security, and can be used to present a specific data structure from the database. They also enable encapsulation of the complexity of the database schema. 4. Updating views. Some views are updatable and can be used in update statements, allowing changes to be made to the base table through the view. 5. Security with views. Views can restrict access to specific rows or columns of data, enhancing database security. They allow exposure of only necessary data to certain users, protecting sensitive information. 6. Materialized views. Unlike standard views, materialized views store the query result as a physical table. They can improve performance but need to be refreshed to remain up to date with the underlying data. Effective use of SQL views. 1. Simplifying complex queries. Views can encapsulate complex SQL queries, making it easier for users to query data without understanding the underlying complexities. 2. Data security and access control. By defining views, you can control access to the data, showing only relevant information to specific users or roles. 3. Performance optimization. Materialized views can improve query performance by storing the result set of complex queries. 4. Data abstraction. Views provide a level of abstraction from the actual tables, allowing changes in the database design without affecting the end user's queries. 5. Consistency in data representation. Views ensure that the same logic is applied each time the data is accessed, promoting consistency in data representation across different applications or reports. Advanced query techniques in SQL. 1. Window functions. Perform calculations across a set of table rows that are somehow related to the current row. Unlike aggregate functions, they do not cause rows to become grouped into a single output row. Common window functions include row underscore number, rank, lead, lag, and over. 2. Common table expressions, CTEs, temporary result sets that are defined within the execution scope of a single select, insert, update, delete, or merge statement. CTEs make complex queries more readable and maintainable. Syntax: with underscore name as CTE underscore query, select from underscore name. 3. Recursive queries. A recursive query is a query that refers to a recursive CTE. It is used to deal with hierarchical or tree-structured data, like organization charts or directory structures. A recursive query typically consists of a base case and a recursive step. Utilizing advanced query techniques. 1. Analyzing data over partitions. Window functions allow for complex calculations across data partitions, like cumulative sums or moving averages, without collapsing rows. 2. Simplifying complex queries. CTEs offer a way to break down complex queries into simpler, more manageable parts, making them easier to understand and maintain. 3. Managing hierarchical data. Recursive queries are particularly useful in managing and querying hierarchical data, allowing for operations like traversing a tree or graph structure. 4. Enhancing readability and maintenance. Both CTEs and window functions contribute to better readability and maintenance of SQL queries, especially when dealing with complex data transformations or analysis. 5. Solving real-world problems. These techniques are essential for solving real-world data problems, such as generating reports, analyzing trends, or processing hierarchical data structures. SQL optimization. 1. Query performance analysis involves examining queries to identify performance bottlenecks. Tools like SQL Server Profiler or Explain Plan in Oracle and PostgreSQL can be used to analyze query performance. It includes looking at factors like join types, indexing, and query execution time. 2. Writing efficient SQL queries. Efficient SQL queries are vital for performance. This includes using proper join clauses, avoiding unnecessary columns in select statements, using where clauses effectively, and optimizing subqueries. Writing queries that minimize the amount of data processed and returned can significantly improve performance. 3. Understanding and using execution plans. Execution plans show how a database engine executes queries. Understanding them helps in identifying inefficient parts of a query. They provide insights into aspects like index usage, table scans, join operations, and the cost associated with each part of the query. Best practices for SQL query optimization. 1. Use indexes effectively. Proper use of indexes can significantly speed up data retrieval. However, indexes should be used judiciously as they can slow down insert, delete, and update operations. 2. Optimize joins. Understanding how different join types work and choosing the right one is key. For example, prefer inner join over outer join when possible, as outer joins are generally more expensive. 3. Avoid unnecessary columns. Selecting only the necessary columns in the query, rather than using select, can reduce the amount of data that needs to be processed. 4. Leverage aggregate functions. Aggregate functions can be used to retrieve summary data and perform calculations. When used properly, they can minimize the amount of data to be processed. 5. Optimize subqueries and CTEs. Subqueries and CTEs should be used judiciously. Poorly written subqueries or CTEs can lead to significant performance degradation, especially in large datasets. Stored procedures and triggers. 1. Writing and using stored procedures. Stored procedures are precompiled SQL statements that can be executed on demand. They help in encapsulating complex logic, ensuring consistency and reusability. They are created using the create procedure statement and executed with the call command. Stored procedures can contain complex logic, take parameters, and return results. 2. Creating and managing triggers. Triggers are special types of stored procedures that automatically execute in response to certain events on a table or view. These events can include insert, update, or delete operations. Triggers are useful for enforcing business rules, maintaining audit logs, and keeping data synchronized between tables. 3. Use cases for automation and data integrity. Stored procedures and triggers are commonly used for automating repetitive tasks, ensuring data integrity, and implementing complex business logic. They can reduce the amount of data sent to and from the database server and centralize business logic in the database. Advantages and considerations in using stored procedures and triggers. 1. Efficiency and performance. Stored procedures can enhance performance by reducing network traffic and reusing execution plans. Triggers can ensure data integrity and consistency automatically. 2. Data security. Both stored procedures and triggers can enhance security by encapsulating database access and logic, limiting direct access to underlying data tables. 3. Maintenance and debugging. Centralized business logic in stored procedures and triggers can simplify maintenance, but it can also make debugging more complex, especially when multiple triggers are involved. 4. Complex business logic implementation. They are ideal for implementing complex business rules and data transformations, which are challenging to manage in application code. 5. Potential downsides. Overuse of triggers can lead to complex interdependencies and performance issues. Similarly, stored procedures might lead to a harder to maintain system if not properly managed. Handling large volumes of data in SQL. 1. Partitioning. Splitting large tables into smaller, more manageable pieces. 2. Indexing. Using indexes to speed up queries on large datasets. 3. Batch processing. Processing data in small batches rather than in a single operation to reduce load. 4. Archiving. Moving older, less frequently accessed data to different storage to improve performance. 5. Optimizing queries. Writing efficient SQL queries by selecting only necessary columns, using joins effectively, and avoiding unnecessary subqueries. 6. Pagination and efficient data retrieval. Using offset and fetch, limiting the number of records returned and offsetting where to start returning records. Syntax. Select from table _name order by column offset X rows fetch next Y rows only. 7. Seek method. More efficient than offset for large datasets. It uses a where clause to fetch records starting from a specific point. Example. Select from table _name where id greater than 1000 order by id fetch next 100 rows only. 8. Caching results. Storing frequently accessed data in cache for faster retrieval. 9. Asynchronous loading. Loading data asynchronously can improve the user experience in applications by not blocking the UI while data loads. Best practices for data management in large datasets. 1. Regular data maintenance. Regularly archiving, partitioning, and indexing data can significantly improve performance and manageability. 2. Effective use of database features. Utilizing database features like materialized views, stored procedures, and efficient indexing strategies. 3. Query optimization. Continuously analyzing and optimizing queries for better performance, especially in large datasets. 4. Scalability considerations. Designing systems with scalability in mind to handle growing data volumes effectively. 5. Monitoring and performance tuning. Regularly monitoring database performance and tuning configurations as necessary to handle large data volumes efficiently. What is a data lake? 1. Definition. A data lake is a centralized repository that allows you to store all your structured and unstructured data at any scale. It is designed to store vast amounts of data in its raw format. 2. Key characteristics: highly scalable, cost-effective, and capable of storing diverse data types, like logs, XML, JSON, and binary data. 3. Storage format. Data is stored in its raw format, not yet processed or analyzed. 4. Use cases. Ideal for big data analytics, machine learning, and storing data that is not yet defined for specific analytic purposes. What is Delta Lake? 1. Definition. Delta Lake is an open-source storage layer that brings reliability to data lakes. It provides ACID transactions, scalable metadata handling, and unifies streaming and batch data processing. 2. Key features. Includes ACID transactions, scalable metadata handling, and schema enforcement. 3. Storage and format. Stores data in a version parquet format, enabling rollbacks, full historical audit trails, and reproducible machine learning experiments. 4. Use cases. Best suited for scenarios requiring high reliability and data consistency in data lakes, such as data engineering, data science, and machine learning operations. What is a data lakehouse? 1. Definition. A data lakehouse is a new, unified architecture that combines the flexibility and cost efficiency of data lakes with the data management and ACID transactions of data warehouses. 2. Key characteristics. Combines the best features of data lakes and data warehouses. 3. Architectural features. Supports a wide variety of data types and use cases, from historical reporting to machine learning, with strong governance and performance. 4. Use cases. Ideal for organizations looking for a single platform to handle all their data needs, including reporting, AI and ML, and real-time analytics. Similarities: data lake, Delta Lake, data lakehouse. 1. Large-scale data storage. All three are designed to store large volumes of data, accommodating big data needs. 2. Support for diverse data types. They can store various types of data, including structured, semi-structured, and unstructured data. 3. Integration with analytics and ML tools. Each can be integrated with modern analytics and machine learning tools, facilitating advanced data processing and analysis. 4. Use in big data ecosystems. Commonly used in big data ecosystems, supporting data storage, processing, and analysis at scale. Differences: data lake, Delta Lake, data lakehouse. 1. Data integrity and reliability. Delta Lake offers ACID transactions and versioning for higher data integrity, unlike traditional data lakes. Data lakehouses provide similar data reliability but within a unified architecture. 2. Performance optimization. Data lakehouses are optimized for performance similar to data warehouses, which is not a primary feature of traditional data lakes. 3. Data governance and quality. Data lakehouses offer better governance and data quality features, combining the benefits of data lakes and warehouses. 4. Specific architectural features. Traditional data lakes are primarily for storage. Delta Lake adds a layer of reliability and performance, and data lakehouses unify storage and analytics capabilities. Data modeling techniques. 1. Conceptual data modeling. This high-level, abstract model establishes the scope and overall structure of data, focusing on the organization of data entities and their relationships. 2. Logical data modeling. Involves defining the structure of the data elements and setting the relationships between them. It is more detailed than conceptual modeling and doesn't involve any physical level details. 3. Physical data modeling. Specifies the physical storage details of the data model. It includes tables, columns, indexes, keys, and other physical database elements. 4. Dimensional data modeling. Used in data warehousing. Involves fact and dimension tables. It is optimized for data querying and reporting, rather than for transactions. 5. Normalization. Process of organizing data to minimize redundancy. It involves dividing a database into two or more tables and defining relationships between the tables. 6. Denormalization, process of combining normalized tables to improve database performance. It adds redundancy to a normalized database to enhance read performance. 7. Entity relationship modeling, a graphical approach to data modeling that represents entities, their attributes, and the relationships between entities. 8. Object-oriented modeling, based on object-oriented programming principles. Data is represented as objects, similar to software objects in programming. Data warehousing architectural models. 1. Single-layer architecture, simplistic and not commonly used. All data warehousing functions are performed in a single layer where raw data is converted directly into a form suitable for reporting and analysis. 2. Two-layer architecture, consists of a staging area for raw data and a separate layer for data storage and query management. This model offers more flexibility than the single-layer architecture. 3. Three-layer architecture, includes the staging area, data storage, and a presentation layer where data is made available for reporting and analysis. It's the most common and offers the highest level of separation for different data warehousing functions. 4. Federated architecture, involves the integration of multiple, possibly heterogeneous data warehousing systems or data marts. It allows for a unified view across different data sources. 5. Hub and spoke architecture, centralized data warehousing architecture where a central data warehouse is connected to multiple dependent data marts. 6. Bus architecture, involves a central bus through which all data flows across the system, supported by conformed dimensions and standardized data definitions. Data warehousing schemas. 1. Star schema, the simplest style of data warehouse schema. The star schema consists of a central fact table referencing a series of dimension tables. It's optimized for querying large datasets and is the most straightforward for end users to understand. 2. Snowflake schema, an extension of the star schema where dimension tables are normalized, dividing them into additional tables. This structure reduces data redundancy but can be more complex and may require more joins. 3. Galaxy schema, or multidimensional schema, a complex schema that combines multiple star schemas or snowflake schemas into a single database. It's used to represent more complex business scenarios and allows for multiple fact tables with shared dimension tables. 4. Fact constellation schema, similar to the Galaxy schema, this schema uses multiple fact tables that are linked to common dimension tables. It's suitable for complex data modeling scenarios, allowing for various levels of data granularity. 5. Normalized schema, a highly normalized data structure, emphasizing the elimination of redundancy in dimension tables. It's not as efficient for querying as the star schema due to the higher number of joins required. Data analytics aggregation techniques. 1. Summation, calculates the total sum of numerical data in a specified set. Commonly used for total sales, total costs, etc. 2. Averaging, computes the average or mean of a set of values. Useful in understanding the central tendency of the data. 3. Counting, counts the number of items in a dataset. Can be used to count occurrences, distinct values, or meet certain conditions. 4. Min/max analysis, determines the minimum or maximum value in a dataset. Useful in finding extreme values like highest sales, lowest temperatures, etc. 5. Group by, groups data by certain columns to perform aggregate functions like sum, average, count, min, and max within each group. Essential for categorized data analysis. 6. Time series aggregation, aggregates data over time intervals, for example, daily, monthly, yearly. Used for trend analysis and time-based reporting. 7. Pivoting, transforms data from long to wide format, making it easier to compare variables and see relationships. 8. Statistical aggregation, involves using statistical methods like standard deviation, variance, etc., for more detailed analysis of data distribution and variability. 9. Cubes and OLAP operations, OLAP, online analytical processing. Cubes allow data to be analyzed in multiple dimensions, enabling complex analytical and ad hoc queries with rapid execution. Common operations include slicing, dicing, drilling down/up, and pivoting. 10. Window functions, perform calculations across a set of table rows related to the current row. Unlike standard aggregation functions, window functions do not collapse rows. 11. Drill down, allows users to navigate through layers of data to explore details at a granular level, often moving from higher-level summaries to more detailed data. 12. Roll-up, the opposite of drill down, it aggregates data along a dimension. Roll-up summarizes detailed data to a higher level, combining data in larger groups. 13. Binning/bucketing, involves grouping data into bins or buckets based on a range or category, often used for breaking down large datasets into manageable groups. Data pipeline stages. 1. Data collection, the first stage, involving gathering data from various sources, which could include databases, file systems, streaming data, and external sources. 2. Data ingestion, involves importing, transferring, loading, and processing data for immediate use or storage in a database. 3. Data validation, ensuring the accuracy and quality of the data. This stage involves checking for corrupt data, incomplete data, or incorrect data. 4. Data processing, this involves transforming raw data into a format that can be analyzed. It may include sorting, aggregating, joining, and otherwise manipulating data. 5. Data storage, storing processed data in data warehouses, databases, or other storage solutions. It's essential for data accessibility and management. 6. Data analysis, extracting insights and patterns from processed data. This can involve complex analytical algorithms and data mining techniques. 7. Data visualization, representing analyzed data visually using charts, graphs, and other visualization tools to make the data understandable and actionable. 8. Data monitoring and management, involves continuously tracking and managing data flow throughout the pipeline and ensuring the system's performance and reliability. 9. Data archiving/backup, storing data in a secure, accessible manner for long-term retention and recovery in case of data loss. 10. Data reporting, the final stage, where data is presented in a structured format, providing actionable insights and decision-making support to end users and stakeholders. Data mart. 1. Definition of data mart. A data mart is a subset of a data warehouse, focused on a specific business line or team. It's a repository of data that is oriented towards a specific business function or department. 2. Characteristics. Data marts are smaller, more focused, and subject-oriented. They are designed to meet the needs of a particular group of users. They are generally easier to use and navigate than full data warehouses due to their specific focus. 3. Types of data marts. 4. Independent data marts, standalone systems designed for specific departments, without integrating with a central data warehouse. 5. Dependent data marts, created from an existing data warehouse and are connected to it, ensuring consistency in data. 6. Benefits include improved response time for data queries, easier data management, tailored to specific user needs, and often lower costs compared to full-scale data warehouses. 7. Use cases, commonly used for specific business processes like marketing, sales, finance, or HR analytics. Ideal for organizations that require a quick and focused solution for data analysis and reporting in a specific area. Change data capture, CDC. 1. Definition of CDC. Change data capture, CDC, is a process used to capture changes made to the data in a database. It identifies and tracks changes in data so that action can be taken using this data. 2. How CDC works. CDC works by monitoring and capturing insertions, updates, and deletions in a database, and then delivering these changes to a data warehouse, data lake, or other systems. It can be implemented using database triggers, log scanning, or real-time replication technology. 3. Real-time data synchronization, captures changes in real time, ensuring data consistency across systems. 4. Minimized load on source systems, efficiently captures data changes without significantly impacting the performance of the source systems. 5. Enables real-time analytics and reporting. 6. Facilitates efficient data replication and synchronization across systems. 7. Helps maintain data integrity and consistency. 8. Real-time data integration, integrating data from various sources into a data warehouse or data lake. 9. Data replication, replicating data across different databases or systems for backup or operational purposes. 10. Event-driven architecture, triggering workflows and processes based on data changes. Data normalization, 1NF, 2NF, and 3NF. 1. What is data normalization? Data normalization is a process in database design that organizes data to reduce redundancy and improve data integrity. It involves dividing larger tables into smaller, more manageable ones and defining relationships between them. 2. First normal form, 1NF. A table is in 1NF if all its attributes have atomic values, meaning each column contains unique and indivisible values, and each row attribute combination contains a single value, no repeating groups or arrays. 3. Second normal form, 2NF. A table is in 2NF if it is in 1NF and all non-key attributes are fully functionally dependent on the primary key, meaning no partial dependency of any column on the primary key. 4. Third normal form, 3NF. A table is in 3NF if it is in 2NF and all its attributes are not only fully functionally dependent on the primary key but also independent of each other, no transitive dependencies. In other words, non-key attributes do not depend on other non-key attributes. Thanks for watching.